So I'm going to talk about Floer Homotopy. And last year I talked about Floer Homotopy as well, and I talked about Spectra a lot. But at some point over the last year, I realized that part of the reason that the subject is essentially incomprehensible is because it's been done from the wrong perspective. And you'll see in a minute what I mean by that. So I will explain a construction of Floer Homotopy groups that doesn't use Spectra at all. Now it will turn out, at the end of the story, once we've constructed them, if we try to understand them, we probably should involve some spectra, and that's not too surprising, because it's a little bit like saying, you cannot do homological algebra without chain complexes, but at least you should be able to talk about the homology groups without introducing them. So where do we start? So the model for Floer Homotopy that is most convenient to think about, kind of abstractly, is this context of what is called the manifold flow category. So let's start here. And this manifold flow category has many variants, but it somehow encapsulates what happens in Morse theory, and it encapsulates what happens in Floer theory in the nicest situations. So this is some kind of, let's call it M. This is a topologically enriched category. And I want the morphisms to be MPQ, the manifold with corners, and then you want to make sure that so they're corners. So that means that you can make sense of the boundary of NPR for objects. So P and Q are objects. You want the boundary of NPR to essentially be given by the product of NPQ cross NQR modulo the obvious gluing relation, which is that if you, so this is supposed to be, the map from this to NPR is just the product, is just the composition in this category. You want to make sure the composition lands in that boundary, but not only that it lands in this boundary, but that the boundary is subdivided into codimensional pieces. Boundary strata are basically given by these compositions. And you have to be, there's small variants of this. You can assume that this is an embedding, or maybe you can assume that it's not an embedding, but we can come back to that later. Okay, so this is the abstract setting, and the key point is that you take a smooth manifold, and let's say f from M to R is a Morse function. Then this moduli space, then you can form a category. Let's call it just M of F. This is a flow category, manifold flow category, with morphisms given by the gradient flow length. Space of gradient flow length. Now, this is in some sense the most simplified example. In Floer theory, what we encounter is something more complicated. Because in this case, I didn't quite say this, these moduli spaces are proper.
Just the objects here will be manifold symmetric.
Sorry, here, so I haven't said it yet.
Critical points?
The objects are critical points.
And you need still some genericity condition.
I should have say Morse smale, I should have picked a Morse metric, I should have, yes. Flow category, so pick a metric. So in this case, in Morse theory, this moduli space is compact. In Floer theory, there are many, many problems that occur, but the first problem that occurs is that the moduli spaces are not proper. So you do the same thing. I'm not going to do the same. Just going to say Floer theory would have the moduli space not compact. But what happens is that you have some kind of Gromov compactness. Gromov compactness can be, let's say, encapsulated abstractly. Encapsulated by one more piece of data. By, let me say it like this: a functor from pi 0 and from the component of this to 0 infinity. And by that I mean, i.e., you have a map from NPQ to 0 infinity, which is constant on components, and compatible with composition. Or composition here is addition. This is like the category with one object. And composition here is addition. And when you have this data, you can just say you would like, such that this map has, so this is kind of discrete image and is bounded, discrete image. All I'm saying is that in the Morse theoretic case, you have compactness, and in the Floer theoretic case, you don't have compactness, you have just kind of this notion of energy, if you think about it. Things are bounded modular. Anyway, so I will try to explain things in this. It's not clear whether it's really worth the time for me to explain things in this general context, because the ideas are already apparent here, but I will refer to it every once in a while.
Yeah, but usually sometimes people go to some coverings and it will be...
Covering is essentially,
It's
ultimately if you pass to a covering, you're passing to create many objects, one object for each one of these. It's not really that enlightening. I think this already incorporates the data that you have, and you don't have to talk about coverings anymore. Okay, so what is the goal? So the goal is to define something like stable homotopy groups of this flow category. And this, we will see in a moment, requires some additional conditions, but maybe we don't want, maybe this is too complicated, maybe we will want like K theory of this thing, okay? And other generalized cohomologies of this. And we have one test case. We have one case where we know the answer, which is Morse theory. Okay? It should have the property so that we recover stable homotopy groups of n, ku of n, etc. If this is not curly n, if the flow category comes from Morse theory. Okay? And that will tell us that we're doing the right thing. And the point is that the current approach in the literature for doing this is kind of crazy. It's basically you solve a gluing problem. Okay? You say, well, I know that if there were no moduli spaces whatsoever, there were no morphisms, then the answers would be a direct sum of direct sum of copies of, let's say, the stable homotopy groups of spheres of ku of a point, indexed by the number of critical points. And then you just say every moduli space gives me an element of, at least the first one gives me an element of this, of the stable homotopy groups of ku and so on and so forth. And then you kind of inductively try to group it. Current approach. So start with the free direct sum of copies of, let's say, power S0 point. Okay? Then introduce some kind of differentials that are encoded by the modulus. And And if there's only one moduli space, the answer is very transparent. But as soon as there's two moduli spaces, it becomes a complete mess to understand. So the goal of this talk is basically for this to become, so this is the opposite of what the goal of most talk. This is now, this is currently the definition. This to me should become a computation. Okay? You should define it in a different way, in a way that is much more transparent, in a way that is not, I take free pieces and I try to glue them together. And having defined it that way, then you can try to say whether you can compute it. Okay? So,
yeah, but Mohammed, but I think it's in Floer series less troubles, it's a bubbles. Yeah?
I will talk about that too, don't worry. So you're worried maybe about Lagrangian Floer theory. Let's for a moment do something like the Hamiltonian case, something related to. In which case the trouble is going to be that we get manifolds instead of manifolds, we get some other notion.
Yeah.
I'll talk about that in a minute. But first I want to understand this. So yes, so this is the goal of the talk. Now there is one more issue to talk about, which is about obtaining these groups. Okay? So we actually know from the current approach and from general principle that we should not expect these groups to be defined unless we assume that we have given ourselves certain orientation data on these moduli spaces. Okay? And so before going further, I just want to talk about the universal case. The case where you don't have to choose any data. No choice of orientation. And again, from this point of view, it should be the case, it should be the theory, the cohomology theory, with the property that all manifolds are oriented with respect to this cohomology theory, okay, without any choice of data. And that cohomology theory is just unoriented bordism. So in the first half of this talk, what I will explain is instead of KU or this, I will explain how to define the object, something which would be called, there are two notations for this, MO over star and M. Okay. This is the homotopy theorist's notation. The geometric topologist notation is this. They're the same thing. They are the geometric, the unoriented bordism groups of flow category. Okay. So it turns out that actually this definition of this bordism group, I've probably known this for about 10 years. I just didn't realize what they were. Didn't realize that they were in fact isomorphic to the ones that would be constructed through homotopy theory. So the way you define them is by simply using our moduli spaces of holomorphic curves. So bordism of moduli spaces of objects of morphisms in this category. So bordism is defined as the quotient of a set by an equivalence relation. Okay? So I will define a set, and I will define an equivalence relation, and that will be this group. Okay? So the set we want to consider let me call them flow modules over M. Okay. And what they are simply, this is an assignment. P goes to, let me use another letter, let me do P, let's do W, P, of a manifold with corners. To each critical point, to each object of our category. And this should have one more piece of, and now we need one more piece of data, because I already said it's a module. You should think of it as a module over this category. So that means with n maps, WP across space of 2, well, this is a manifold with corners, so I'm going to write a boundary of WQ. Okay? This is manifold. That's manifold. This is I think of as the action of the morphisms in the category on these on these modules. And then you want one condition. Boundary of W of Q is the union of these spaces that I just wrote modulo the obvious relation, which is the relation if you take two morphisms in N, you can multiply them together, and then you can act, and then, or you can multiply, only act first and then the second time, then those should be identical. Okay? So this forms a set. Okay? This set has a canonical operation called disjoint union. This is a abelian monoid under disjoint union. The zero object is the trivial assignment of the empty thing.
This manifolds are abstract manifolds that sits in some huge infinite dimensional.
They don't sit anywhere, they're abstract manifolds.
Yeah.
Okay,
No,
you can object to the fact that it's
yeah.
a set. Okay, I take your point.
Yeah.
I will, let's make them sit in R infinity if you would like,
Yeah.
or let us fix an inaccessible, whatever, yes. Under disjoint union, the empty manifold WQ equals empty set is the zero object, zero element. So if we were in this Floer theoretic context, we would want to impose one more condition, well, one more piece of data. So let's call this Floer theoretic, let's give it a name. The Floer theoretic context, let's call this a filtered. Filtered flow category. So there's, in the filtered case, we can also, we need to, we equip W with a map R. Okay, I don't want to pick it to lambda. I don't want to pick to zero infinity. I want to pick it to R. Q. I want this map to be constant on components. Components bounded below, and with discrete image.
Sorry.
Yes.
W depends on
WP, oh, sorry, WP. Okay. And then, of course, you want to assume that the following diagram commutes, which is that basically this thing, which is going to be your notion of energy. So you have this WP, I have this MPQ, it goes to WQ, this goes to R, this goes to R cross 0 infinity. Here you have addition. Okay? Condition you want to impose. So this is this abelian monoid. And now I can do what I want to do, which is define my Bordism groups as equivalent classes of define my unoriented Bordism groups as equivalent classes. And you define of M to be the Bordism classes of elements of flow modules. And to be what that means is, you know, in this definition I said, you know, the boundary of WQ is essentially covered by the product of these compositions. And more generally, if you take a Bordism, so from W1 to W2 is, well, it's an assignment, let's call it W12. It is also a module, so choice of W12 and P, with maps like this. Also a flow module. But the equation that it satisfies, is just a little bit more complicated. And when you take the boundary of W12 let's do this one, of Q, okay, it consists of two pieces, W12.
No, before you have a map to boundary.
Yeah, the same thing. I mean, the boundary maps to the thing, so okay. It's given by this map to the boundary. But the key thing is that the disjoint union of these over all P, the union of these over all P doesn't cover this. You have one more piece. You have the boundary of this consists of two pieces, three pieces, consists of W1 of Q, it consists of W2 of Q, okay? And then these images. Union over P of W1T, P cross P. That's the notion of a bordism. And this is kind of a standard thing in geometric topology that once you introduce manifolds with, the reason you introduce manifolds with corners is so that you can make sense of bordism between manifolds with boundary. Okay, and that's what's happening.
So I cannot read this.
This says, okay, erase. So the boundary, so W12 is supposed to be a bordism from W1 to W2. So when I evaluate it at any object, I get this. I get this. These are two pieces, okay? And then I also have the pieces that came from the composition, from the other critical points. This is a union over P of W12 of P across the morphism spaces. And the picture you should have in mind is that, it's very hard to draw something like this, but okay. So this is W1, this is W2, and then there's some extra boundary lives over the interval that is the composition. Okay? So I want to point out some obvious facts. First obvious fact is that in the case which is not filtered, so in the unfiltered case, this thing is a module over the unoriented bordism of a point. Okay? And that's just because you can just multiply everything in sight with a closed manifold. You multiply P, W1 of P and W2 of P and the cobordism, everything. Equations do not care. Okay? The way I have set it up, if you instead look at the filtered case, everything is a module of this thing. Is a module over, still is also a module over this, but you have a little bit more room. It's a module over the Novikov range, like Novikov field, on the bordism group. Novikov. Small, yeah, okay. So it is, in fact, an ungraded module, isn't it? Because I didn't say anything about that yet. Okay. And this is an ungraded. But the reason this is the case is basically you just think of, if I give you a series like this, okay, with coefficients in bordism group, you just think of it as the disjoint union. So you just so an element in here. I can think of this as kind of a disjoint union of a collection F lambda I. I mean, it's horrible, horrible notation. Let me call it X. A disjoint union of Xi's, okay? And Xi is a manifold. And then the map to R is given by is whatever the valuation here.
to
Yes.
suggest so that when consider this form power series rings, there's also possibility to co-exponents to form not a single infinity, well-ordered sets.
If I knew where that appeared naturally in Floer theory, I would introduce that. Yes, I understand. Yes,
Yes.
it is appealing to somehow think in that generality. Yes, but right now, I don't know an example. So that's it. And now comes the first time where there is some kind of. So far, this is just the definition is very appealing, very easy to define. There's in some sense no hard work. And the first piece of hard work is when you try to compute this. Okay? And now I will make a statement, and let's call it a conjecture because nothing I haven't sat down and really proved anything yet. Quite good. So conjecture.
It's hard to read the red.
Okay? So yes, it's clearly hard to read because it's supposed to be orange. Conjecture, I will not rewrite conjecture, which is that there is a spectral sequence with E1 term, actually I think this is E2 term. The cohomology, I'll explain in a moment what I mean by this. With F2 coefficients. Tensored over F2 with complex Borgesian point. An E infinity term. What I called the Borgesian So the reason that, okay, so first of all, what do I mean by cohomology and with coefficient F2? What I mean is that the way things have been set up, the way things are set up, what you can do is you can just ignore all the moduli spaces which have dimension bigger than 0, okay? And then you can just introduce a chain complex, and the chain complex is going to be one generator for each critical point, and the differential is going to be multiplied by the number of elements of the zero-dimensional moduli spaces lying in NPQ. That's a chain complex. The proof is a chain complex is because when you compose, you should see something which is a boundary, and therefore the count is 0. Okay? So that's what this is. And now, unoriented Borgesian of a point is a module over F2. That's just because a manifold and a manifold is two copies of a manifold is null cobordant because of this picture. So this is why. This is the F2 module structure. And so, at least now the statement makes sense. Okay? The thing that we call Floer homology, or Moore's homology of the left, is this part here. You tensor it with this ring, and you get this thing. And so I do not. I basically, this is where not having spectra doesn't help. Okay. So somehow I don't, it's probably possible to prove this without spectra. This is a version of the T-Hertzsprung spectral sequence. So if you understand that well enough, you can probably prove it by hand. But in practice, what is really happening is you can identify, and if I have time, I'll explain this later, you can identify these groups with some homotopy groups of the spectrum that you can construct also using geometry. And if you filter that spectrum, you will see that as the first page. Questions before I keep going? Okay, so in the so this spectral sequence is convergent in the non filtered case. In the filtered case, I'm not so sure, and in fact, I expect that it's not convergent. So now what I want to do is I want to talk about some variants of this story. So the variants of this story, they all have to do with taking this low category and equipping it with more data. Okay, I would really like to have a different color at this stage. The first variant is the one that already appears, well, the one that would be kind of most natural to discuss. we should have some Z grading. Okay? We can assume, so we say that, so equip M with a Z grading. I mean, maybe you can be, this was crazy. I didn't even have Z-mod 2 gradings. The only reason that's kind of reasonable is because I didn't have orientations. But you can equip M with a Z grading, i.e., you can have a notion of degree of P for every object. And then when you do this, you want to assume, and the dimension of MPQ is now going to be the degree of P minus the degree of Q minus 1. Okay? In this context, you can then study graded modules. Okay? So for each n, I can look at assignments of manifolds. So we can define, so now I'm going to stop using the star. The nth group of M of this flow category comes from assignments WP, where now this has to be a manifold of dimension n plus the degree P. Looks right to me. Okay? N plus the degree P. Okay? So now this thing you do modular boundary, you do modular Bordism as before. So this is the story that is somehow more familiar, because this story, the Homotopy theorists would have called it something like periodic unoriented Bordism. That's the first thing. The second variant is to put a little bit of more structure on these moduli spaces. So choose orientations. So people, in geometric topology, people call it G structure. Stable G structure. And what it means is, for example, the simplest one to do is an SO structure, compatible orientation. So that's G equals SO. Okay? And so what this will mean is, instead of having an unoriented Bordism group, you will have an oriented Bordism group. It's usually called Mohammed. Yes. I got unreal. I don't want to keep writing.
There was some.
Yeah, I'll grab all the
Let's see this.
Okay, so so there'll be oriented Bordism groups. Nope, that doesn't work either. That's even worse. Oh, good. So the oriented Bordism groups, G equals SO of this thing. And again, like before, you have conditions of this nature. But I want to keep going. So the next case you could do is you could G equals U. Okay? And you get stable complex orientation. And maybe I'll write this omega U of M. And I want to point out that this case is particularly important in symplectic topology. In symplectic topology, because if your flow category is coming from Hamiltonian Floer theory, that is, if you don't have Lagrangian boundary conditions, you're doing some kind of absolute theory, you always have this kind of data. Okay? And the last case I wanted, of course there are many cases, there's many groups you could write down. The last case I want to talk about is G equals the trivial group. Okay? And the point is that G equals a trivial group has a name. It gives you frame Bordism. Okay? And frame Bordism is isomorphic to stable homology, stable homotopy. So the answer to the question, how do you define homotopy groups, stable homotopy groups of the flow category, is you study the frame Bordism groups. And this, again, this is exactly the in the definition, the Cohen-Jones-Siegel, when they first introduced this, they assumed that all the moduli spaces, all the morphism spaces were stably framed, precisely so that they could do this. So what is happening? Why are these constructions so much simpler? It's because we are working on the geometric side of the Pontryagin-Thom construction. Okay? The previous constructions were all done on the homotopical side of it. And the homotopical side of it is very good for computations, but not very good for constructions, especially if your construction is coming from geometry. Working on the geometric side of Pontryagin-Thom. Okay? 3. So the third thing I want to talk about is the thing that Maxime objected to, which is that when you do Floer theory, you don't encounter manifolds. Okay? You don't encounter manifolds, you encounter something else. But whatever it is that you encounter has a Bordism theory. So if instead we assume has morphism spaces that are orbifolds or that are, say, Coronation spaces. Then you can just do the same thing. And what you can do is you can take, well, the morphism spaces are like this, so it better be that your modules are of the same nature. And look at modules of the same nature. And the output is going to be, I'm going to put orbifold here, orbifold Bordism groups of that, and Coronation Bordism groups of that. So I want to point out one feature that occurs when you do this. And it's not apparent. I mean, it's a feature both of these theories, but it's less apparent in the orbifold theory. So in the orbifold theory, at first sight, this would look like a connective theory in the sense that the geometric definition, simplest geometric definition of orbifold Bordism group, point, has the property that it vanishes for negative degrees. If you can just say, I'm going to look at orbifolds on the boundary, and if they're orbifolds like this, then the manifold, there's an underlying manifold mod G. So for negative degrees, you get nothing. Okay, but in fact, there is another theory of orbifold Bordism you can define. Let's call it homotopical Bordism. Even though, and let me call it, I don't want to use homotopy theory, but theory. Let me just call it let's do this. M word. Okay. Which is not connective, which has non-trivial elements in negative degree. And the way you should think about it is that instead of just taking orbifolds to build your homology theory, your homology theory, instead of just taking orbifolds, you should look at orbifolds equipped with a map to a sphere with a non-trivial group action. And this is something that you should assign not to V, but to the point. And the virtual dimension, so then this is an orbifold. And this is a generator of orbifold groups. These theories are better behaved. This theory is kind of more complicated than this theory because it has elements in negative degree, but it has better behaved, let's say, algebraic features. It has better Poincare duality, isomorphisms, and so on and so forth.
So you try to think something like manifold plus vector bundles.
Plus vector bundles, yes, but somehow all the vector bundles is taking place in this direction. You just have to add one copy of this vector bundle. And the point is that if this V is a representation of G, if you look, for example, at the origin, okay, that maps here, but it's not. It doesn't come. If it's an isolated fixed, if it's somehow that's the only fixed point, then that becomes an element in negative degree of your homotopy theory. You cannot count. Okay. So now the reason I introduced this is because of the next conjecture, and that's exactly what makes sense saying. Well, not exactly no, but there's a relationship between these two things. So put another conjecture. Let's call this equivariant transversality. Stable equivariant transversality. Which is simply that the Kurnishi-Bordizin groups of a point are isomorphic to these homotopical Bordizin groups. Okay? That in some sense, the complexity of Kurnishi-Bordizin is, it is very complicated, but it can be encapsulated in understanding just orbifold part and one vector space that is the target of your analog of your obstruction bundle. You don't need to understand complicated vector bundles. So this conjecture, I think at this stage is provable. The only kind of argument for proving it that I know uses quite a bit of machinery, kind of existence of global charts, some classical work in equivariance transversality. But so I'm optimistic that this will work out. Okay.
Can you remind what is Kurnishi?
Oh, what is Kurnishi? Kurnishi. Well, okay. So, what is Kurnishi thing? That is a good question. So, a reasonable definition, okay, which is in fact relies on a theorem, okay, is a Kurnishi space is going to be is going to be a compact orbifold equipped with an orbibundle. Okay, and the point is that in general you cannot pick a section of this orbibundle to get a zero locus. But let's have that as a working definition of this. Compact Bordisms of compact manifolds, or compact orbifolds with orbibundles on them. Okay? And so the question is, why does Floer theory give rise to such things? Well, I was just talking to Bernd and explaining that in his work on Gromov-Witten theory, he basically explained that moduli spaces in Gromov-Witten theory can be described by this feature as compact orbifolds with vector bundles on them. Okay, that was 3. How much time do I have? 16. Thank you. Okay, 4. So there are some theories. There's one theory that people like that is not in this list. Okay, I mentioned Bordism. I mentioned other kinds of Bordism. But one theory I didn't mention was KU. Okay, so this can be obtained. So again, the key point to observe is that we are producing a homology theory. Okay, we're producing a homology theory, and KU, complex vector, but K theory at first is a cohomology theory, but it can be obtained in exactly the same way. the homology version of it by considering, well, instead of these M's, instead of these W's being just manifolds, you do the next step by considering modules, which are pairs W, E, okay, I will skip this one more piece of data you need, but anyway, this is now a spin C manifold, and this is a complex vector bundle. Okay? And the W is going to behave just like before. The complex vector bundle is just going to be carried along for the ride. And then the only thing that I want to say here is that this, of course, only makes sense at first if the moduli spaces MPQ have spin C structures. Otherwise, again, you're not entitled to do this. So you can take Bordisms of such things. It doesn't quite work. There is one, if you only take Bordism, you get too many, you don't get enough relations. There's one new relation, which is that you pass from, you kind of make W and E equivalent to the Tom space of E over W, which basically means the sphere bundle of E direct sum 1. Okay, and then to pull back of it. So this is some relation that you have to put in so that you don't have too many kill generators that correspond to each other. So this works well in the manifold case. Okay. Oh, so this has a name. This theory has a name. It's called K homology, topological geometric K homology. It was invented by Baum.
I think I got lost because when considers per manifold, the bundle and effective dimension will be different. Manifold minus rank, yeah?
Yes, that's
and here it's kind of,
yeah. So yeah, in the Konishi theory, there is something. Here, what you do is that for K0, you look at W being an even dimensional manifold,
yeah.
And for K odd, W is an odd dimensional manifold, and that's it. And that's why the theory becomes
no
two
grading,
periodic.
okay.
No grading. So it better be two periodic because this is two periodic. You only have even and odd grading. Okay. So this is the classical theory. This works well. As I said, for manifold flow categories. Okay. But then you can do the same thing. Replacing W by an orbifold. Or replacing W itself by a Konishi space. You can do the same. Replacing W by orbifold or Konishi space. And now I'm going to state a conjecture. After replacing W by W, even if W is not a manifold, this theory still gives rise to K theory. Still get KU with more general W. And I'll explain. General W. So this is a special feature of K theory. So the point of K theory is that, equivariant K theory is extremely well behaved. Okay? So orbifolds have fundamental classes in equivariant in K theory. They don't have fundamental. The core spaces of orbifolds have fundamental classes in K theory. And similarly with Konishi spaces are just built from manifolds and vector bundles. So from orbifolds and vector bundles, you build a fundamental class in K theory on the orbifold part, and then you cap it against the class of the vector bundle. And one way to interpret this, so conjecture that you can do this. One way to interpret this as the existence. This is something that people are not going to doubt very much. So just like there's a map from MU, okay. So MU is complex Bordism. This maps to KU. This is some kind of Todd class. Okay? The claim that I'm making is that this map, in fact, factors through several steps. One of them is, I'm just going to write orbifold bordism, complex orbifold. And then factors further through complex Kurenishi space, stable complex Kurenishi bordism. And that actually maps here. So the map that we're familiar with manifolds can in fact be done with orbifolds just as well, and can be done with Kurenishi spaces just as well. Okay? So the outcome of this is that, if you do this, and if this conjecture is correct, then you have yourself maybe not as simple as things were at the beginning, but it's still a relatively transparent and geometric definition of, so from this, we get a geometric definition of Floer K-theory. Okay? Because while the Kurenishi bordism groups are maybe, I probably don't ever want to have to compute them. I don't think anybody ever wants to compute them. But they have maps to things we understand. And one of the first things, the main thing we understand is KU. And so they still have map to KU. Now, just a small advertisement, which is that there's been this work, I've been still not released. So with Blomberg, we have some work on Morava K-theories, work on Floer theory with coefficients in Morava groups. Okay. And, unfortunately, it is not going to be written in this language. It's going to be written in whatever language we wrote it in. But you can interpret that in this language. You can interpret as exactly this thing. In fact, this is in some sense something we proved. So there's a map from MU to KN that is somehow the definition. Part of the definition of these Morava groups is that they are complex oriented, so they have a map from KU. But in fact, this map factors through all these groups, and then we can take kind of Kurenishi bordism. So if you construct something where the moduli space, this is exactly what we prove in this paper. If you construct a flow category in which the morphism spaces are Kurenishi spaces equipped with stable complex structures, okay, then from that you can extract a KN homotopy type. Except our proof, instead of working on the side of Pontryagin-Tong that I'm talking about today, worked on the other side.
If I remember correctly, Morava C depends also on prime number.
Yes, there's a prime and a number. Yes, for each prime, for each any prime.
Okay.
For each prime, for each height. So n is the height and p is the prime. I don't know where to put the p. For all p prime and natural numbers. Not union infinity. No, and natural. P prime. Okay. Yes. Okay. So now that I only have 5 minutes, maybe even less. 5 minutes. Good. So now I will talk about spectra. Okay. So the point is that this construction was without spectra. But if you want to go a little bit further, what you really want to do is you want to not, especially once you get to K-theory is still fine, but when you want to get past K-theory, do something which are, start becoming quite abstract. You don't want to formulate the theory as, there is a bordism, blah, 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 blah. What you want is, you want to construct a spectrum, okay, which is a module spectrum over the spectrum that corresponds to Kurenishi bordism, for example, or the spectrum that corresponds to, let's say, MO. Let's step back and stop talking about Kurenishi stuff. Okay? You want to work with chain complexes. Because if you work with chain complexes, this factorization immediately gives you what you want. So what you want is to find Floer homology groups. Generalized homology groups. So E lower star of M Okay? For each homology theory, E equipped with a map from whatever Bordism theory worked for you. So I'm going to just write Bordism, where this is the Bordism theory over which things are defined. Bordism theory of the moduli spaces NPQ. Okay? If they're unoriented, it's just unoriented Bordism. If they're oriented, it's oriented Bordism, and so on and so forth. If they're Kurnishi spaces, it's Kurnishi Bordism, whatever it is. Okay? So each thing which is equipped with a map, where this is a map of spectra. You could say of cohomology theories, but let me mess that up and say it's the same thing. How would you do this? It's tautological. E of M should be defined as the homotopy groups of E of the spectrum omega of M. And I'm going to write tensor, maybe people would write smash, tensor over the theory omega with E.
So it should not have the structure of module.
Sure, it does not need to be a ring. Yes. I'm assuming that E was a ring, but you are right. You are right. With a module structure, that's a better thing to say. Module structure over omega, where this is the Bordism theory that moduli spaces live in, and you would define it by this equation. And the point is that this should be a spectrum. Okay? Well, in fact, so for a manifold case, this is actually quite easy to do. And this is why I had this discussion of like who is connective and who is not connective. We could do it for both of them, but it's just easiest to do for the manifold case. So the point is that we can indeed construct a spectrum, but in fact we can construct a space, we can construct an infinite loop space. So this next part is joint with Plummer. And hence probably the only thing that's ever will get written. So step back for a second. This joint union. So I have 5 minutes. So what can I say? So let's consider simplicial set whose n simplices are W over delta n. Okay? Where what is this? This is a flow module. So what does this mean in practice? I.e., you want to equip your maps, WP, with maps to delta n, and you want to make sure that if you take WP cross of MPQ, mapping to WQ, this is compatible with the projection to delta n. Okay? It's not quite a simplicial set. Only the way for this to be a simplicial set is for you to assume that, in fact, this projection map is transverse to all boundary strata. Once you impose this, you have all the desired properties. You can restrict by just looking at the inverse image of a stratum, and that defines a simplicial structure. Okay? This thing defines a space. But in this space, we have disjoint union, okay, with a monoid structure. Commutative. Commutative. Monoid structure. Well, this is something that people know very well. This is what is called an infinite loop space. And hence it gives rise to spectrums by standard machine. So all I'm trying to say is that everything that I explained today, I said it was without spectra. But in fact, if you want spectra, all you have to do is do the same thing parametrically over the simplices. Okay? This works, this does what you want for the connective theories, and this is for kind of manifold case. if you were doing with a non-connective theory like orbifold Bordism or the Konishi case, or maybe KU, you have to be a little bit more careful. You have to introduce just one more piece of information, which is that you want to work parametrically over all spaces. Okay. You just introduce an extra parameter, and then you can just show that this will also give you a spectrum. Okay, I will stop here.
Questions? So that is incorrect. Is that in Floer theory really you need only this Konishi story and orbifold to introduce just because it's simpler to understand?
Yes.
Yeah.
Yes.
Okay.
So
But there's no technical role at all. Yeah. So.
well, I mean, there are some places in Floer theory where some very special places where you encounter orbifolds. But if you want the general Floer theory, no, you're just Konishi spaces is where you're trying to go. And orbifolds are just there to kind of make it into two-step process. Yes.
More questions?
So all these things about simplices, it's kind of like a different situation of algebraic geometry. You can
Yeah.
see the cycles and even can transversal to the simplices algebraic sense.
Yes.
Like log and yeah.
I'm sure it's the same intuition
it's
ultimately.
similar.
You know, you want some notion of chain complex, but you don't know what a chain complex is, but you can talk about families over delta n. That's your replacement for a chain complex.
High groups, it's very similar definitions.
Mhm.